Hey there, this is Mathcamp321, and we're still talking about different operations that we can perform with natural logs. In number 8, we're asked to expand the natural log of the square root of x cubed over the fourth root of y. To start, I'm going to perceive the argument as a quotient and implement the quotient rule. As a result, we get the natural log of the square root of x cubed minus the natural log of the fourth root of y. My next step will be to convert each argument into an expression using a rational exponent. For my third step, I'll implement the power rule or the power ranger rule and allow those powers to become the coefficients of the respective terms. Having done those manipulations, I realize there are no more properties that can be implemented, so this problem is now completely expanded. Let's move on to the next slide. On this slide, we're asked to condense a natural logarithmic expression. You might recall from a prior video that our strategy is to implement the power rule in reverse if possible. In other words, if there are any coefficients in front of the natural log expression, to allow those coefficients to become the powers of the respective arguments. And in doing this, we'll end up getting the natural log of x plus 1 to the 1/2 power minus ln2 to the power of 2 minus the ln of x to the power of 3. In the next step, I'm going to look at the first term and rewrite that using a radical, and in the second term, I'm just going to evaluate 2 squared as 4, and the third term I'm just going to leave alone. Now, taking the terms 2 at a time from left to right, I'll start to slowly condense from 3 natural log expressions down to 2. Because what we have here is a difference of logs, I know this can be condensed into the natural log of a quotient. And in transitioning to my final step, I realize that again I have a difference of natural logs, which will turn into the natural log of yet another quotient. The age-old question being, where is this x cubed going to end up? Will it end up in the numerator or will it end up in the denominator? Why don't you take a guess and write something down before I reveal the answer? So this problem has now been fully condensed. We started off with a natural logarithmic expression in 3 terms, and we've got it down to a single natural log. Let's move on to the next slide. On this slide, we're going to talk about the change of base formula. The change of base formula as it pertains to natural log is just going to be a slight add-on to what we already know about the older change of base formula. We learned in a prior video that the log of a base b can be rewritten as the ratio of common logs log of a over log of b, in which the base ended up in the basement. Well, it just so happens that even if your initial expression is in logs, you can also express this as the ratio of natural logs. So the log of a base b can also be thought of as the ratio of the natural log of a over the natural log of b. Again, the base still ends up in the basement. To convince ourselves that this new format of the change of base formula works, we're going to compare number 10 and number 11. In number 10, we're asked to rewrite the log of 34 base 2 as the ratio of common logs and then determine the decimal approximation. Let's go ahead and do that now. The log of 34 base 2 can be thought of as the log of 34 over the log of 2. If you do this on your calculator, you end up getting a decimal of 5.087. If we go to number 11 and we rewrite the same problem as the ratio of natural logs, we end up getting the natural log of 34 over the natural log of 2. If you go to your calculator and you figure out that quotient, you end up getting the same exact thing. Thus proving it doesn't make a difference which version of the ratio you use. You can convert something not of base 10 to the ratio of common logs or to the ratio of natural logs. Either way, you're going to get the same thing. Let's move on to the next slide. On this, the second to last slide and the last slide, we're going to look at a few examples of how to solve equations involving natural log. In number 12, we're asked to solve 24 natural log of x equals 8. To start, I need to isolate the natural log expression, which means I need to divide both sides by 24. This will result in the equation natural log of x is equal to 1/3. Our implied base is e, so I'm going to go ahead and write that in, and then I'm going to perform the all-important swing. Starting at e, swinging up to the right to the 1/3 and landing on the argument of x. This reveals the equivalent exponential form of e to the 1/3 is equal to x, or if you prefer, x equals the cube root of e. In number 13, they're asking us to solve 10 times e to the power of 2x minus 1 equals 35. Again, there is this idea of needing to isolate before I start, so I need to get rid of that 10 before I can begin. If I divide both sides by 10, I end up with, at this stage, I can take the natural log of both sides. Now this is the first time we're seeing this, but in a prior video we were taught that we could take the log of each side. In this case, I'm going to take the natural log of each side. And the reason I'm going that route is because we're dealing with a base of e. So it just makes more sense to use natural log in this case. For my next step, I'm going to use the power rule and allow the power 2x minus 1 to leap down in front of the ln e expression. Because it's a multi-termed power, I'm going to use parentheses. In our following step, I'm going to take note of the fact that the ln of e is actually just the number 1. If you do a quick swing and ask yourself e to what power equals e, we know that that is going to equal 1. For that reason, the only expression remaining on the left side is 2x minus 1. To begin the isolation process, I'll add 1 to both sides. And finally, I'll divide both sides by 2. So my final answer is x equals 1 plus the natural log of 3.5 divided by 2. This would be considered the exact answer. Let's move on to the next slide. On this last slide, we're going to look at two last examples of solving equations involving natural logs. In number 14, we're asked to solve the natural log of x minus the natural log of x minus 1 equals 4. I'm focusing on the left-hand side and I'm thinking that I'm going to condense. We have a difference of natural logs, and this is going to turn into the natural log of a quotient. In our next step, we have an implied base of e, so I'm going to do a swing. Writing the power of e in, we're going to start at that little base of e, swing up to the right, and land on this more complicated argument, revealing an equivalent exponential form of e to the 4th equals x over x minus 1. Putting the left side over 1, we have a clearly identifiable proportion for which I will cross multiply. In my next step, I'll distribute the e to the 4th through the parentheses. In my next step, I'm going to have an x party on the left side. In other words, all terms that have an x will go to the left. All terms without an x will go to the right. Next, I'll factor out an x from the left-hand side. In my last step, I'll divide. It's important for at least a moment to consider what the value of this fraction would be, and think about if you were to take the decimal approximation and plug it back into the original, if your argument would still be positive. If it's positive, then you're good. If it's negative, you're going to have to reject that answer because the argument of any natural log expression needs to be positive. Now I've done the legwork for that, and I know that the answer is going to be a good answer, so we're going to leave that. I'm going to leave it up to you to do that check if that's something that you want to do. Moving to number 15, the first thing that I'm going to do is again condense on the left-hand side. But this time we have the sum of two natural logs. This is going to turn into the natural log of a product. The product of x plus 2 and x minus 2 can be thought of as a more simplified expression, x squared minus 4. In my next step, I'm going to remove the natural log from each side, leaving me with x squared minus 4 is equal to 12. Since this is a quadratic equation, I'm going to solve for x by moving the 4 to the other side, leaving me with x squared is equal to 16. Now I'll take the square root of both sides, leaving me with x equals plus or minus 4. Considering the check for each of these questions, I'm going to consider what would happen if I put positive 4 in for x. We would end up getting the natural log of 6 plus the natural log of 2. And that does in fact equal the natural log of 12, so that works. If I were to check by plugging in the negative 4, we would have a problem because we would have an argument that is negative. And the minute you have an argument that is negative, we have to reject that answer. So the true answer is x equals 4 only. So on the last two slides, we saw 4 examples implementing different solving techniques involving natural logs.